Hello all, welcome to the second video from section 4.1. This video is all about subspaces. And the idea, is that often vector spaces appear inside of Rn or inside of another larger vector space. We have a special definition for just that. It is the definition of subspace. So a subspace of a vector space V is a subset H with the following three properties. We need that 0 is an H. We need that H is closed under addition, which just means anytime we've got two vectors in H, their sum is also in H. If U and V are in H, then so is the sum. And similarly, we need H to be closed under scalar multiplication, which means if C is a real number and U is some vector in H, then CU is also in H. These properties are enough to prove that that H is a vector space in its own right, with all of its operations inherited from V. So let's look at some examples. For any vector space, vector space V, V is a subspace of itself, and so is sort of the boringest possible example of a vector space, the set just containing 0. Right, and how do we check this? Well, that V is a vector space comes from the definition of, we know that 0 is in V because V is a vector space. We know that V is closed under addition because that's part of the definition of vector space, and also closed under scalar multiplication. Again, both of those, or all of those, coming from the definition of vector space. That 0 by itself is a subspace. It's sort of boring because yes, 0 is an H. It is closed under addition because the only two vectors we have are the 0 vectors, and sure enough, the 0 vector plus the 0 vector is the 0 vector, so it is closed under addition. And it's also closed under scalar multiplication because any scalar times the 0 vector is still that 0 vector. So we cannot leave our, we don't leave the set containing only 0 by either addition or scalar multiplication. So it's a subspace. Let's look at a more interesting examples. Maybe let's let bold face P be the set of all polynomials in one variable, say. In one variable with real coefficients. So we can show that P is a vector space containing Pn. Remember, recall this was the set of polynomials of degree no more than n. So this contains Pn for all n. It contains Pn as a vector subspace. As a subspace. It's true for all n. Let's do a quick non-example, because this is a common mistake to make. So R2, perfectly good vector space, but it is not a subspace of R3. And there's a subtle distinction. And the idea is just that, well, here we've got pairs of numbers. Here we've got triples. It's not even a subset. It's not even true that every pair of numbers is automatically a triple. Now, there's some way of putting R2 inside of R3, but there's lots of ways of doing that, right? If we're living in R3, we can have R2 like this. We can have R2 like that. We can have it like this. There's lots of ways of putting R2 inside of R3 for sure. But as like, there's no copy of R2 inside of R3. And the idea is, so let's write down some of what I just said. This is because vectors in R2 are pairs of numbers and vectors, oops, in R3 are triples. So R2 isn't even a subset of R3, I should say. Okay. However, so let's talk about subspaces of R3 that do look like R2. So we'll say, however, we could look at H, which is the set of vectors of the form maybe S, ST0, with the property that S and T are real numbers. I mean, maybe this is what you're thinking of when you're talking about when you want R2 to be a subspace of R3. We just sort of like conveniently forget about the third number. Yeah, so this is, yes, the set H is a subset of R3. Yeah, that is very similar. Very similar to R2, but not equal. Very similar, but not equal. Okay. We can show H is a subspace of R2, or of R3, sorry. And there's nothing special about making the third coordinate 0, right? We could say, S0T, X and T are real. This is also a subspace of R3. And this is part of what I was saying before. There's no one way of putting R2 inside of R3. There are many, many ways. Oh, right. But we do need our subspace needs to contain the 0 vector. So it's not that any plane in R3 is going to work. We need a plane that passes through the origin, not just any old plane. Okay, let's do a more careful example, maybe. So let's let V be all of R2. We'll let U be in V, and we'll let H be what? Every multiple of U. And our claim is H is a subspace. So let's carefully go through this and show why this is the case. So to show that H is really a subspace, we need to show these 3 things. We need to show that 0 is in our set. We need to show that if any 2 things are in our set, so is their sum. If we grab any vector in our set and any scalar number, then the scalar vector product is also in our set. So let's just go ahead and roll up our sleeves and do just that. So 1. Yeah, we know 0 times U is equal to the 0 vector. And we know 0 times U is in H, because H is a collection of all multiples of U. And so this gives us that the 0 vector is in H. I guess we don't need that check mark, but that's the first thing we needed to check, that the 0 vector is in fact in our set H. Next, we need to grab any 2 vectors in H and show if their sum is also in H. So let's let U and V, or not U and V, I guess we'll take X and Y. U vectors in H. We'll show X plus Y also in H. Okay, so since X is in H, yeah, then by definition there is a real number C1, so that X is equal to C1 times U. Or that's just the definition of H. The only things in H are multiples of C. So if X is in H, it must be some multiple of C. We're calling that particular multiple C1. And then similarly, oops. Yeah. There is a real number C2, so that Y is just C2 times U. Oh, we didn't do the page. Oh, there we go. So then X plus Y is secretly C1U plus C2 times U. And now, since we know a little bit about arithmetic and even these abstract vector spaces, we know that we can factor out our U. So this is C1 plus C2 times U. Now, we know that the sum of any two real numbers is still a real number, so this is a real number. So this whole thing is just some real number times U, which has to be in H, because we know H is the collection of all real numbers times U. So this implies, yeah, so since, oops, C1 plus C2 is a real number, it must be that C1 plus C2 U is in H. And so all of that means that X plus Y is in H as desired. And then finally, we need to show that any scalar multiple of any vector in H is also in H. So let's let X be in H again. And we'll let C be, let C be a real number. Okay, again, as before, this means X is equal to like some C1 times U for some real number C1. But this means that Cx is equal to C times C1U. And we know from our little bit of, from our definition of vector space that the order of, or how we parenthesize these things doesn't matter. So this is the same as C times C1U. And again, since this is just the product of two real numbers, we all know that the product of two real numbers is still a real number. So this is just some real number times U. So since C1 is a real number, it must be that C1 U is in H, but that just means that Cx is in H as desired. So since H satisfies 1, 2, and 3, it is a subspace of R2, or of V, I guess. Oops. Okay, and more generally, yeah. There's a more general example in the textbook. Given v1, v2 in V, the span of these two vectors is always a subspace. Okay, and then details for this in the book. It's a good book. Okay, we'll capture this with our first theorem of the chapter. Theorem 4.1: if v1, v2 up through v, what happened there? Why is that looking so funny? Oh, I see what happened. There we go. If v1, v2 up through vp are vectors in a vector space V, then H, the span of these vectors, is a subspace of V called the subspace generated by v1, v2 up through vp. Okay, so that's a quick summary of the example we just did. Again, we'll leave the proof for the textbook if you're interested. Let's do another example. So let's show H, which is a set of triples x1, x2, x3, such that x1 plus x2 plus x3 is equal to 0. Let's show this is a subspace of R3. Okay. So again, we should check that the zero vector is in H. We should show that H is closed under addition, which means if we grab any two vectors in H, the sum is also in H. And we should show that H is closed under scalar multiplication, which means if we grab a vector and a scalar, the product is also in H. So the zero vector. So notice the triple 0, 0, 0 satisfies the equation. x1 plus x2 plus x3 is equal to 0. So our zero vector is in H. Boom. Done. That one's usually pretty easy. Okay, so let's let U and V be in H, and then we'll show U plus V is 2. Okay, so then if U and V are in H, this means U is equal to like U1, U2, U3, and V is equal to V1, V2, V3. And what? If they're in H, it means that they have to satisfy this equation. So we have these two equalities, that U1 plus U2 plus U3 is 0, and V1 plus V2 plus V3 is 0. And notice these aren't vectors, right? This isn't a vector equation. U is the vector with these coordinates. Okay. I'm saying that half for myself so that I don't accidentally put a little arrow over that U3. Good. But what are we trying to do? We're trying to show that the sum is also in H. So we should be looking at the sum of U1 plus V1. Yeah, we should be looking at, well, yeah, look at what happens. If we add these two equations together, we get what? U1 plus U2 plus U3 plus V1 plus V2 plus V3 is equal to 0. But let's group these as U1 plus V1 plus U2 plus V2 plus U3 plus V3 is equal to 0. Oh, but this means what? The vector U1 plus V1, U2 plus V2, U3 plus V3 satisfies our equation, x1 plus x2 plus x3 is equal to 0. But this vector is just equal to the vector u plus v. V. Okay, so our u plus v satisfies the equation. That means u plus v is also in H. Okay, so we've got that it contains 0. We've got that it's closed under addition. It remains to show that it's closed under scalar multiplication. Oh. So finally, let u be in H, and we'll let C be a real number. So we know that if u is in H, yeah, u is equal to some u1, u2, u3, with the property that u1 plus u2 plus u3 is equal to 0. But this means that cu1, cu1 plus cu2 plus cu3 is equal to 0 just by multiplying both sides of our equation by c. But this means that the vector cu1, cu2, cu3 satisfies our equation. Satisfies. There we go. But this vector is just exactly cu. So cu satisfies our equation, which means that cu is in H. Okay, so since our subset H satisfies 1, 2, and 3, it must be a subspace. Right, this proves H is a subspace of R3, rather. Boom. Oh yeah, okay. So this was a little bit of work, slightly painstaking. Let's prove the same result using this new theorem. So in other words, if we can show that H is actually the span of some vectors, then theorem 4.1 really quickly shows that it must be a subspace. Okay. Let's use theorem 4.1 to prove the same result. Boom, happy face. Okay, so H is still the set of all triples x1, x2, x3 with the property that x1 plus x2 plus x3 is equal to 0. Okay, so this means that no matter what x2 and no matter what x1 and x2 are, we have that x3 is just minus x1 minus x2. And so this means these triples, if we look at them like vectors, we can write them as x1, x2 minus x1 minus x2. And this is giving us some idea of how to express H as the span of two vectors, because look what happens. We get back x1, 0 minus x1 plus 0, x2 minus x2. And if we take out like those scalar quantities, 1, 0, negative 1, x2, 0, 1, negative 1, we get back exactly H as the span of two vectors. So this means H is equal to the span of these two vectors, 1, 0, negative 1, 0, 1, negative 1. And so by theorem 4.1, H is a subspace of R3. Okay, so there's the brute force way of doing it with your own two fists or whatever. And here's the much quicker, I think, way of doing it using this theorem 4.1. Okay, that's all I have for you from section 4.1. I'll see you next time with section 4.2. Take care, everybody.